So your code isn't working. You might think it's just a bug, but for this, we're going to treat it like a full-blown crime scene. To solve the case, we're putting on our detective hats and unmasking the 3 usual culprits responsible for all the chaos. You know, it's a great question, because when something goes wrong, both the programmer and the detective are staring at a puzzle. They've got to sift through evidence, follow clues, and use pure logical deduction to figure out not just what went wrong, but why. All right, detective, let's get to it. We've got a report of a misbehaving program. And the first step in any investigation, you've got to know who you're looking for. In the world of coding, we have 3 prime suspects who are behind pretty much every case. And here they are, in the lineup. First up, we've got the clumsy culprit. That's the syntax error. Then there's the unpredictable menace, the runtime error, who loves to cause a scene. And finally, the most cunning of them all, the silent assassin. That's the logical error, the one who works in the shadows. Let's interrogate them one by one. First in the interrogation room is suspect number 1, the clumsy culprit. This is your classic amateur. Not very subtle, and they leave evidence all over the place. A syntax error is basically a grammar mistake. You know, you misspelled a keyword, you forgot a semicolon, or you used the wrong punctuation. The computer, which is a very strict grammar checker, just looks at your code and says, nope, I have no idea what you're trying to tell me. So the program won't even start. And this right here is exactly why this culprit is the easiest to catch. See, the compiler, it acts like a security guard, stopping them right at the front door. It just halts the whole program and often points you directly to the mistake. Case closed before it even really begins. Another classic move by this culprit is messing with identities. In programming, we call them variables. But for our investigation, just think of them as labels on evidence bags. If they aren't labeled according to the rules, the whole operation just falls apart. And this slide shows you exactly what I mean. On the left, you've got valid names using letters, numbers, and underscores. All good. But on the right, that name 3 apples, that's a dead giveaway. You can't start an evidence label, a variable name, with a number. It's like a forged ID, and the compiler spots it immediately. All right, let's move on to suspect number 2, the unpredictable menace. Now this culprit is a lot smarter. Their grammar is perfect, so they slip right past that security guard, but once they're inside, that's when they cause chaos. So what even is a runtime error? Well, it means the code starts running just fine, but somewhere in the middle of doing its job, it gets asked to do something impossible. And at that exact moment, the program basically just throws its hands up in the air and shuts down completely. It just crashes. And here's some of this suspect's signature moves. Asking the computer to divide a number by 0? Yeah, that's mathematical nonsense, and the program will crash. Trying to grab the 5th item from a box that only has 4 things in it, that's an index out of bounds error. It's a plan that looks perfectly fine on paper, but it fails spectacularly out in the real world. And now we come to our final, and by far the most dangerous suspect, the silent assassin. This is the criminal mastermind. They leave no obvious trace, no warning signs, and no crash report. They are a ghost in the machine. Take a look at this piece of evidence. The syntax is flawless. The instructions are completely valid. This program will run without a single complaint from the system. But hidden inside this seemingly innocent code is a devastating, hidden flaw. So the code executes, it starts its task and enters a loop, and then it just keeps going, and going, and going, forever. It never actually finishes its job. There's no crash, there's no error message, just a program that's stuck. So what on earth went wrong? And here's the crucial point. The computer is doing exactly what you told it to do. The problem is that your instructions were flawed. You, the detective, made a mistake in your logic, and the computer just followed your flawed orders perfectly, leading to the wrong result. So how do you catch a silent assassin? How do you find an error that doesn't announce itself with a loud crash? Well, you need to upgrade your toolkit. You have to start thinking like a true master detective. You can't solve this kind of case just by staring at the code. No, you have to get inside its head. You have to become the computer and reenact the entire process, line by line from the very beginning. In programming, we call this essential detective technique hand tracing. And it's a beautifully simple yet really powerful method. First, you set up a table to keep track of your key variables. Think of them as your persons of interest. Then you walk through the code one command at a time, just like the computer would, manually writing down how the value of each variable changes. You're literally creating a paper trail to follow. Okay, let's actually put this into practice. Our crime scene is a piece of code that's supposed to sum the digits of a number. We've set up our investigation board just like on the slide, with columns for our variables, n, sum, and digit. We'll start by writing down their initial values. N is 1729 and sum is 0. Now we follow the code's first move. It calculates the last digit, which is 9, and adds it to the sum. Then it updates the number n. We record everything. We cross out the old values and write in the new ones. See, n is now 172 and sum is 9. The trail of evidence is starting to form. We just keep repeating this process, meticulously tracking every single change. And here, on this slide, we see the final state of our investigation. The loop has finished, and we can clearly see the final value in our sum column is 19. The mystery is solved. By manually tracing the steps, we figured out what the code actually does, not just what we thought it would do.
So there you have it, the three main culprits behind every coding crime, and the master technique to catch the most elusive one of all. Let's close this case file with one final clue. This right here is the most important lesson for any code detective. It's really the core of the job. Your logic is on trial, not the computer's. The clues are always there. You just have to know how to look for them. And more importantly, how to spot that difference between what you intended and what you instructed. So I'll leave you with this to think about. The clumsy culprit gets caught right at the door. The unpredictable menace causes a loud, obvious crash. But the silent assassin? It works quietly, corrupting your results without ever making a sound. So which one should a good detective really be worried about?